So welcome. So last time we started touching on using Newton's laws and the like, and we talked about the force law of gravity, and I made the point that we can talk about it in terms of its magnitude, and we can talk about it in terms of its vector form. And I made the point that I don't particularly like this vector form because it's like you got to know the order that the subscripts go in, and then if they're not in the order of the subscripts, what do you do, and all this kind of stuff. And it works out. The book's very clever. It works out. But my sense is you might as well just look at the diagram and basically decide which of these two forces I'm asking you about, and decide which way the vector is that I give you. So maybe I give you it where it's pointing to from the red one to the blue one, or maybe I give it pointing from the blue one to the red one. And then you compare the direction of this displacement vectors with the direction of the force that you're interested in, and if they're in the opposite direction, you put a negative sign in. And if they're not, you don't put a negative sign in. It just makes so much more sense there. So yeah, this is the equation that's in the book that people quote. It's got this negative sign in there, but the negative sign in there is because of what they choose. They say the force in this direction with the unit vector in that direction. So they're deliberately making it in its opposite direction, which is why they have the negative sign there. But you might not do that. I might not ask you that. I might give you them both in the same direction. I might give you that. I might ask you about that force and give you that direction, in which case there is no negative sign in there because they're both in the same direction. So the diagram really is much better. The G, of course, that's just Coulomb's constant. Not Newton's constant. It's the universal constant of gravitation. And we did this example, didn't we? Okay. So let's now talk about gravitational field strength. And so the question I have for you is gravity only there when you get two objects? Do you need two masses to get gravity? So, let me say it a bit more clearly. Do you need two objects to get a gravity force? For sure, yes. Forces, two objects, two forces, equal and opposite, yes? Now, when I say gravity, it's one of those awful terms where it's like, what on earth do you mean by gravity? And frankly, I don't know what I mean by gravity. I can tell you the latest model. Particle physicists will say there's these things called gravitons going off in all directions. But we've never been able to find a graviton, and you never run out of gravitons, and quite what they do is not so clear. Well, it's not actually, it is quite clear actually what they do. They mediate between the two particles. If you have I think I explained this, if you have a skateboarder with a bag and he throws it, he veers off that way. If he catches it, he veers off that way. So the bag acts as a mediating particle causing a repulsion. When you look at the outside and you can't see the bag, all you see is these two skateboarders go away from each other. They're repulsed. But they're repulsed by the transfer of the bag. And I don't know how you do the opposite. If I threw a helium balloon to you, would we go this way? I'm not sure we would, but we might. But anyway, you can have repulsion, you can have attraction. So, okay, I'll buy in. There's these mediating particles, which is the gravity. So, if there are these mediating particles that is giving rise to gravity, do the mediating particles only get emitted when there's a second object to receive them? What do you think? Do you think the Earth is bright enough to know, oh yeah, there's the moon over there, so let's send some mediating particles? Or do you think it's just going, oh man, I'm losing mediating particles? What do you think? Is this object emitting gravitons all the time, no matter what? Or is it emitting gravitons because there's other masses around? Is it a bright pen? Has it got senses? Does it perceive? There's people. Let's send some mediating particles. What do you think? No, it just sends them out. It just sends them out. And so the gravity effect, if you like, these gravitons have been sent out. happens whether or not there's an object there. If you're this little pebble in the middle of interstellar space with nothing for a couple of light years around, you'll still be sending out these mediating particles. You're not getting any back, but you're still sending out those mediating particles. You don't feel a force because you're not receiving any, but you're still sending out these mediating particles. And you will forever, and you'll never run out. You know, okay. So that raises the issue of gravity. Force needs two masses. But the gravity effect, gravity, you know, I don't know what I mean by just when I say gravity, but, you know, it's like, it's a bit like saying blue, you know. I mean, blue is a color. Gravity, force is a type of force, you know. You can't just have blue. You've got to have something that's painted blue, or you've got to have something that's emitting blue. You can't just have blue. It's like, what, it's an adjective or something? And gravity, to some extent, is kind, I don't know if it's an adjective or my wife's going to kill me when I get home. But it's one of those, like, you know, it's not a thing in itself, it's a type of thing. So when I say gravity, so we can imagine this thing, it's very imagined. There's this thing called gravity, which is the emission of the gravitons, and it happens whether or not there's another object there. And how do we talk about this thing? And we start talking about fields. And whenever I say a field, if you were to describe to me a field, and I'd never seen one, how would you describe a field? Not, I mean, just a colloquial field, not a science field, but a field, literally a field. It's an area and of something. Does a field necessarily have anything in it? No, not really. You know, you can have a field of maize or, you know, a field of corn, but if you just say a field, you can't have this picture of a grassy bit, you know, with walls around the edges and all that kind of stuff. There's space. And so they start talking about gravity fields. And it turns out this is, on one hand, a very simplistic concept, so that if you're not careful, you go, that's nothing. So you miss it. On the other hand, it can like suck you in and you can be like, man, this is like the weirdest thing I've ever come across. But it is so useful that pretty quickly we stop particularly referring to forces as our thing, and we start preferring to talk about fields as our thing. Because if I know the field strength at any point in space, I can tell you what the force is for any mass you put there. If I know the field strength here is 15 newtons per kilogram, and you give me 1 kilogram, that's 15 newtons. If you give me 5 kilograms, that's going to be 75 newtons. If you give me 2 kilograms, that's 30 newtons. It's a general way of characterizing the gravity effect at that point. And it's more useful than the specific case of having two masses. It's like a map, really. It's like, you know, you can look at a map of the terrain around a mountain, and it tells you the contour lines and all that kind of stuff. And it's really useful. It's like, you know. So that's the game we're going to play now. So when I did it, I thought, oh, who needs this? So I kind of blew it off. And it was only later I thought, man, this is like really valuable. And why do we keep talking about fields? Why does this professor now talk only about fields? You know, and it's like, because then I was disconnected. Now they're talking about fields all the time, and I'm still thinking, well, how does that relate to forces? Oh, there's no mass there. There's no force, but there's still a field. How can that? Because I'm stuck on forces. So what we do is we have to have a charge. I keep saying charge because this comes up completely again in physics too. We spend a fair amount of time on it. So we have a mass. So here's the mass, and it's setting up a gravitational field around it. In all directions, there's gravitons going, if you like. And we pick a point, and this, I'm sorry, you know, how do I show a point that's not a particle and all this kind of stuff? And what I say is, okay, there's a point in space, and that point in space has a gravity field like a gravity field strength associated with it, and that will be measured in newtons per kilogram. And what's the relationship between the gravity field strength and the force? Well, what I really should say, and you've said it a whole bunch of times, you said W is equal to mg. And what you're really saying is that the force is equal to the mass times the local gravity field strength. That's really what you're saying when you say that. Not mass times acceleration. You're probably told it was mass times acceleration, but you're really saying it's the force times the gravity field strength. And if I have a mass and it's causing a field and I want to know the field strength at one point, what I could do was I could put a known mass at that point and measure what its weight was. Because then I could say, well, my field is equal to the force that's felt by a specific mass. Okay? So I can do simple stuff. I can give you the field and ask you for the force. I can give you the force and ask you for the field. I can give you the field and the force and ask you for the mass, you know. And that's in magnitude terms. But I can also do vector terms because the field has a direction. It points in the same direction as the force will point. Because if you look at that, the direction of the force is the same as the direction of the field. So then I can say, well, hold on. Magnitude-wise, my field is equal to big G times m over r squared. Where did that come from? We said our force was equal to big G, big M, little m over r squared. And I said my field is equal to my force over the mass that's in the field. So then I go, well, that's going to be big G, big M, little m over r squared, little m. And those little m's cancel. So that equals big G, big M over r squared. That's where that comes from. So the only difference between the force and the field is one of them's got big M and little m, and the other one's only got big M, you know. And then I can talk about my vector gravitational field, and it's just going to be this magnitude multiplied by a unit vector, you know, etc. And again, you get that from the diagram. So we can say an 8.2 kilogram block experiences that. So here's my block, and this is 8.2, and it experiences 13.3 newtons of weight when located in space near planet Zebron. Somewhere in space near this planet. What's the magnitude of the gravitational field? So my gravitational field magnitude equals big G, big M over r squared. Do I actually give you a distance? Oh. What is the magnitude of gravitational field at that point in space? Oh, I'm sorry, this is a nonsense question. I'm giving you the magnitude of the gravitational field strength. That's what that is. I'm sorry, no. No, I'm sorry, no. Just ignore me, ignore me, ignore me, ignore me. I'm just like messing up completely. Which equals big F over M. I was about to tell you there's two different equations. You've got to get the right one. So to illustrate it, I got the wrong one. So which one of these do I use? Oh, yeah. G is equal to big F, which is 13.3, over the mass, which is 8.2, which equals, get my handy dandy calculator out and clear everything, 13.3 divided by 8.2 is equal to 1.62. 1.62, and it's going to be newtons per kilogram. So it's that. It's A. Cool. So that, if you knew the big M, which is the mass of the planet Zebulon, and you knew the distance from this point to planet Zebulon, you'd use the first one, yes. And we're going to do actually a little bit of that here. So now we have Earth, and we have a point. There's no mass here, but there's a point in space, and it's on the surface of the Earth. I want to find G here. So it's not that I'm putting a mass there and saying how much does it weigh. I'm just saying here's a point in space. So I'd say, well, G is equal to big G, big M over R squared, which equals, for the sake of it, FG over M. So we keep reminding ourselves of it. And this equals, G is equal to, what was it? 711? 6.7 times 10 to the minus 11 times M, and M is the mass of the Earth. Well, I give you the mass of the Earth there. 5.98 times 10 to the 24 over, and now you're on the surface of the Earth, but your distance to the Earth, as far as this equation is concerned, is not 0. The point is on the surface of the Earth, but you got to, some of the mass that's pulling this, some of the mass that's creating a field where you are is it's an entire Earth distance away. And some of it, like it's in the middle of the Earth, so it's one Earth radius away, and some of it's right near you. So you've got to average all that out. And so I've got to say, well, this stuff over here is really far away, and that stuff over here is near. Oh, I'll take it the middle. We always take things from the middle because of symmetry. So there's my R. So that would be, I'll give you that as well. 6.37 times 10 to the 6, and that's going to be squared. So G is equal, and this becomes a kind of calculator problem where you go 6.7 second e to the minus 11, enter. And then you say times, and you go 5.98 second e to the 24, enter. So I've done the top line. And then I got two choices. I can do it the traditional way, which is you go 6.37, you divide by 6.37 second e to the 6, enter, and then you divide again by 6.37 second e to the 6, enter. And I'm getting 9.8. Oh, that sounds familiar. I'm getting 9.87. Well, okay, they're the numbers. 9.8 newtons per coulomb, newtons per kilogram. And isn't that what we've learned over and over again? We call it 10 in this room. Isn't it like 9.8 newtons per kilogram? That's where that comes from. That's where that comes from. So what do you think they did? Do you think they massed the Earth and then figured out what the gravitational field strength was? Or do you think that they knew the gravitational field strength, they knew the radius of the Earth, and then they figured out the mass of the Earth from that, When do you think they first knew the radius of the Earth? Was it 100 years ago, 500 years ago, 1,000 years ago, 2,000 years ago? Did Neanderthal man know the radius of the Earth? I walked around and counted steps, and, How long ago do you think it is, just roughly speaking, Who's going to give me an answer? 100? 1,000? Probably 2,000 to 3,000 years ago. 2,000 years ago, probably. Democritus? No. Eratosthenes was a librarian in Alexandria in Egypt. He spoke Greek, and he might have been Greek and moved there, but all of that was occupied by Greece, so it's kind of like but he was in Alexandria. And he read this story about how if you go to Thebes, basically, which is further south, on Midsummer's Day, the wells had no shadows on the walls. You could see right to the very bottom, and you could see yourself reflected in it. And normally there'd be a shadow there. So we thought, that's interesting, because I've never seen that at my house. So we went to his house, and sure enough, on Midsummer's Day, there was a shadow. And he realized, oh my word, if there's no shadow there, but there is a shadow there, that means that the sunlight, which is coming down from above, is casting a shadow here. And, oh man, this means that if I line things up and I can figure out what there's my shadow. If I can figure out what the shadow angle is, then I can work out what angle that is at the center of the earth. And if I pay somebody, and he paid somebody to walk between Alexandria and Thebes and count the number of steps. Can you imagine? It's about 100 miles. Count the number of steps and then come back and remember that number. I'd have written it on my wrist, but come back and tell him it's so many steps, which is so many strata, I guess it is. And he was able to work out the circumference of the earth. You know, if it's 60 degrees, that's 1/6 of the earth's circumference. If it's 10 degrees, it's 1/36 of the earth's circumference. Worked out the circumference of the earth, and from that you can get the diameter and all that kind of stuff. So 2,000 years ago at least, they knew the diameter of the earth. It's fascinating. How long ago do you think they knew the diameter of the moon? 100 years ago, 200 years ago, 2,000 years ago? 2,000 years ago! Because they looked at a lunar eclipse and they said, oh, look, there's the shadow of the earth. Oh, look, if we just draw it and we know that radii, then we can figure out what that radii is. So 2,000 years ago, they knew the radius of the earth. They knew the radius of the moon. How long ago do you think it was that they knew the distance to the moon? 2,000 years ago. He took a coin, and he held it up to the moon until it was like it just covered the diameter of the moon. And then he said, that diameter to that distance is the same as that diameter to that distance. I know that diameter, I know that distance. I know that diameter, I can work out that distance. 2,500 years ago. Yes?
My physics teacher asked us last year, he was like, so we worked out a problem to find the radius of the earth. And he was like, if the sun is setting, and you're sitting down, and you see the sun dip, and then you stand up, and you see it again, and you count 12 seconds for the sun to just
go down.
What is the radius of the earth? I had no idea, so we worked it out. I think it was the same.
Very cool. Very cool. I never tried that. I'll try that. That's very cool. Very cool.
How did they do the gravitational constant, though?
The gravitational constant, big G?
Right, so you're saying that they found the radius, okay. So how would you figure the mass?
That's what I'm saying. Is
Okay, so, right, but then how do they know little g, you know what I'm saying?
Oh, no. I'm sorry. I see what you're getting at. No. What they can do is they can do... let me pause for a minute and think.
Okay, how would they figure each variable?
Big G. So let's have a look. If I use the weight over the mass and I find little g, and I know the radius, I got to find big G. And big G came from our old friend Cavendish. And it wasn't until 1798.
Right, but you need the mass to Earth then.
Or what he did was he took two big lead spheres and two small brass spheres, and he hung the brass spheres via a fiber or a hair. So there's a slight torsional effect on them. It doesn't want to spin. It's not like a wound thread that'll spin forever. You have like a hair or a glass fiber will do it. It will bend, but it doesn't want to bend. So it will fight you. It will want to go back. And what he did was he moved these big heavy spheres and he measured the deflection as it was attracted to one side. And he invented this thing which is called, they used it a lot, it's a light It's basically well, the most common instrument that has them is a moving coil galvanometer. There's one in my office. It's basically, if you want to measure very small movements of something, you don't want a needle on it because the needle has its own inertia. You put a mirror on it, then you shine light in, and a small fluctuation sends the light across through an angle. And because it's light, it goes in a straight line, and you can have light going, 40 feet. So when I was a student, in every room, in every lab, there'd be a moving coil galvanometer over there, on very high up, and you'd have wires so you could connect your apparatus to it. They'd have a light over there to shine into it, and then on that wall, they'd have a big scale. And when you turned the thing on, the thing would be reading like 17, and then and it would go to 47, and you'd figure out what that meant. You have to calibrate and everything. So that's what he did. He put a little mirror on here, shone a light in, looked at the deflection. So there's a very small deflection, but he can measure it. And then for symmetry, he takes that all the way around and all the way around. So now the big lead spheres are pulling the other way. So if there's any asymmetry in the wire, if it wants to go one way but not the other, you average it out.
So you figured big G, and then you figured big R, and you figured radius, and then how do you find little g?
You just... So basically, on this thing, if you...
Don't have mass, remember.
Pardon?
You don't have mass yet, remember.
No, he's trying to find mass.
Correct.
So what you do is, no big G, you know R, you know that.
How do you, that's what I'm saying, how do you know little g?
Oh, you know little g because 1 kilogram weighs 10 newtons. Yeah, from here. You know the weight, W equals mg. You know the weight, you know the mass. Not the mass of the Earth. This is the little mass. So I do an experiment. I say, let's work out the gravitational field of the Earth at this point. And I go, well, this is 1 kilogram and it weighs 10 newtons. So that means that little g must be 10 newtons per kilogram. Now I say, okay, now let's apply that to this other experiment where now I'm talking about a point near the surface of the Earth, and I'm saying, well, look, now that's the mass of the Earth, that's the radius of the Earth, and that's my 10 newtons again, newtons per kilogram. So now I find my big G. Yeah, cool. So I know my big G from Cavendish, so now I find my mass of the Earth. Yeah. So it's 2 experiments. Very nicely done, though, isn't it? Cool. So, first problem. F is equal to, let's just talk in terms of magnitudes. They're so similar, people get them confused. So you've got to put them side by side and compare and contrast them. They are both inverse square relationships. If I double my distance from the mass that's causing the gravitational field, I will feel a quarter of the force. If I double my distance from the mass, the point I'm at will have a quarter the gravitational field. So they're both inverse square. One has 2 masses involved, the parent and me, and the other one has only the parent and the point. So they're similar enough that you get them confused if you're not careful. You've got to put them down side by side and compare and contrast them. Then the next thing we're going to do is we're going to start playing some games. And we're going to say, well, if I take a force and I move it by a distance, what do I get? What is F dot D? It's work. Oh, work is changing energy. What kind of energy am I changing when I talk in terms of heights? Potential energy. So I get this relationship where I say delta U, G, the change in potential energy, which is equal to the work, is going to equal my force, which is that. It's over r squared times the distance. So the distance and one of the r squareds is going to cancel. Now that doesn't justify what I'm going to do next, but it kind of like hand-wavingly does. So I get an expression that looks like that. And the important thing is it's a big M, little m over r, not over r squared. So if I double my distance from the Earth, if I take an object and move it twice as far from the Earth, it will have it will have twice the gravitational potential energy. Okay, not 4 times, yeah? And then I can do something which I say, well, that's kind of useful, but I need both masses in. I'd like to be able to just pick a point and say, what's the gravitational field at that point? But I'd like to be able to say something about energy at that point. And so I have what's called the gravitational potential, which is, we're going to talk about delta Vg, and that would equal Gm 1 over Rf minus 1 over Ri. So we got rid of, can you see the top line has M1 and M, big M and little m in both cases? And its bottom line is only big M. And this left-hand side has 1 over r squared, and the right-hand side has 1 over r. So there's a symmetry, and if you know that pattern, you won't make as many mistakes. If you try and remember 4 very distinct equations that all sound similar, you'll get them confused all the time. That's what I found. Students were always getting these confused. It was like, so from a teaching point of view, it was awful. And yet, when you put them down side by side and you try and distinguish between them, you don't get them confused. Okay? So we're going to talk about that next one, the gravitational potential energy, delta Ug, potential energy, next. And it's important. Potential energy, it's a thing. It's not potential, it's potential energy. They're different things. And so what we have here is we have a mass, and we're going to move it from one point to another point in some haphazard way. And what we're going to find out, of course, is when we're close to the parent, then we're going to have a big pull of gravity on us. But when we're far away from the parent, we're going to have a little pull of gravity on us because we're further away. So it's all right me saying that delta Ug is equal to work, which equals to F dot D, but this is a variable force as distance changes. So I need the vectorial, I need the calculus form. Delta Ug equals minus the integral of Fr dr. Fr is a thing. It's not F multiplied by R, it's Fr. It's like Fr dr. So I have all these little dRs and I want to integrate them. So I say, well, hold on, my Fr, my thing called Fr, is equal to minus G big M little m over R squared. We did that before. Let's just shove that in. So I say my change in kinetic energy and gravitational potential energy is equal to minus the integral of minus G big M little m over R squared dr. And so this gives me G big M little m. They're all constants. Take them outside. The 2 minuses make a plus. Integral of 1 over R squared dr. Well, that goes to minus 1 over R. So I end up with this expression, delta Ug is equal to, and, oh yeah, so I do the minus, so 1 over R squared is R to the minus 2, which becomes R to the 1, minus 1 over R. So that minus comes out of the integration. It's not from these 2 signs here, it's out of the integration. So I have minus, and let's do the final minus the initial. So, boom, 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 boom. So, boom, 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 boom. So we get it. So we say an 80 kilogram mass is located at the origin. So there's the 80 kilogram mass origin. Determine the potential difference, potential energy difference. I'm sorry, I've got to be careful about that. Potential energy difference when a 5 kilogram mass moves from a point defined by that to another point. I'm just using my IJK to give you distances. You know, I'm just saying, okay, that's 2 steps. That's 8 steps. I'm just saying that's 8 and that's 2. I'm just using the IJK to let you draw a diagram, basically. So then I say, okay, well, let's have a look. We said delta UG, I'm sorry. UG was equal to, what did we say? Let's look at our equation, minus G. I've got a little alarm bell going off, but it's okay, I'm going to ignore it for a minute. Minus G, big M, little m, 1 over our final minus 1 over our initial. So delta UG is equal to minus G, leave G alone, and this will be big M. Big M is going to be the 80 kilograms. But I do need this second mass because I'm talking in terms of potential energy. So I've got to have a second mass. That's 5 kilograms. And then 1 over the final, which is 8, minus 1 over the initial, which is 2. Doesn't matter the direction. All that matters is how far you are away. So delta UG is equal to 5/8 of 40. That's 400 G. And that's 1 over 8 minus 4 over 8. So delta UG is equal to minus 400 times, times minus 3 over 8. Delta UG is equal to plus. That goes into that 50 times plus 150 G, if I got my big G. Joules. It's that guy. Now, let me, okay, we'll just go on, okay. Now I'm going to talk about it. So, hold on. Where did I stay? It says what's the potential energy difference between, yeah? Determine the potential energy difference when a 5 kilogram moves, from a point that's 2 to a point that's at 8. Now, let's talk about this gravitationally. Your UG increases as you go higher, is that right? So if you're 2 points away, if you're 2 steps away, you're here. And if you're 8 steps away, you're there. So your gravitational potential energy is going upwards, delta UG. Agreed? Is that a positive change or a negative change? And so I'm happy. It's like a positive change. And it's worthwhile just looking. If you're not asked for the magnitude, it's worthwhile just looking and saying, is that working out the way I expect? Because it's easy to get the signs backwards. This is fine, but it tells me about a specific masses experience, not about any masses experience. The nice thing about fields is they work. They're about the parent. They're not about what you put there. You can put something there and you can work out what's going on, but they're about the parent. So it'd be nice to have something to do with energy about the parent and not about the mass. It's like, let's say we go camping. Let's say we go hiking and we climb, Mount Vesuvius. Nice volcano type thing. And you want to know how challenging it's going to be before you see it. What am I letting myself in for? You never seen pictures of Mount Vesuvius? What would you ask me to get a gauge for how tough it's going to be to climb this mountain? How long it doesn't take. Now, you can ask me how long I take, and supposing I'm a fell runner, so I'm a world champion. So what are you going to do about that? I'm going to say, well, it takes me 20 minutes.
Elevation.
Pardon?
Elevation.
So yeah, so it's got to take into account the difference between us. Yeah, so that's the problem. That's the problem when that's the problem. Yeah. The other thing you could ask is elevation, and then you say, well, okay, that's better because it might take me 20 minutes to climb 3,000 feet. Maybe it takes you a day to climb 3,000 feet, but at least you got the elevation so you can figure something out. So there's this desire to have something, a measure, which is independent of you, which you can then interpret, rather than a measure which is of me, which then you have to depack. You have to say, well, it cuts him that long, so that means that it was going to take me that long. There's a comparative thing there. So it's nice to have numbers that are just dependent on the mountain. And the problem with force is it's not just dependent upon the parent mass. And the problem with change in potential energy is it's not just dependent on the parent mass. So we say, well, rather than talking about forces, we'll talk about fields. And rather than talking about change in potential energy, we'll talk about change in potential. And in both cases, the electric field is the force per unit mass, and the electric potential is the work per unit mass. So it's kind of useful. It's kind of like very nice. So we invent this thing called called gravitational potential. And electrically, when you go to a battery store and you want a specific battery, you probably give them a number, yeah? You give them a letter. You go, I want A's or triple A's, or I want D's or whatever, yeah? How much voltage do they have? Anybody know what's a triple A got? Oh, well, physics 2. It's 1.5 volts because of the chemistry. You get a 9-volt battery. That's not the same chemistry. That's not got a letter, has it? You say, I want a 9-volt battery. It's not got a letter because it's not part of that same sequence. When you say 1.5 volts or 9 volts, what are we saying? Which do you think has most doability? A AAA or a 9 volt? 9 volt. For 2 reasons. One is you don't know how much energy it contains, but I'll tell you this much. A 9 volt battery delivers 9 joules of energy for every coulomb of current that passes, whereas a 1.5 volt battery delivers 1.5 joules of energy for every coulomb. So for every coulomb passing, you're getting what? 6 times more energy from a 9 volt battery than you are from a AAA. So there's more energy density and, etc. So it's kind of really useful. So we deal with voltages all the time in electricity. We're just not so used to talking about it in gravitational things. So here's gravitational potential energy. And what we say is, well, look. The gravitational potential energy difference, where's my pen gone? Potential energy difference was equal to that. And what I could do is I could say, well, let's start off. Oh, so then what I could do is oh man. Okay, I'm sorry. I'm gonna go here. Gravitational potential. I'll come back to this bit. So well, no, I got to go back. I'm sorry, I just misread this. This is gravitational potential energy, not gravitational potential. So look at this diagram there. So that's the gravitational diagram for a mass. And as we go further away from the mass, we get different potential energies. It takes so much to let you get that far away. And it takes more to let you get that far away. And it takes more to let you get that far away. It takes more to let you get that far away. What you notice is as you go further and further away, the pull of this gravity object becomes less and less. So it takes you less and less work to get a next step away. And eventually it's taking you no work to get to the next step because you're in free space and, you're kind of floating around. But until you're floating around, it takes you work to get that little bit higher. Yeah? Less and less work. The hardest piece of work is to get the first step up, and then it's less, and then less and less, because you're going further and further away. So we worked out that to work out the change in my gravitational potential energy equal G big M little m over R over times 1 over R final minus 1 over R initial. And there was a negative sign in there, I seem to recall. Yeah? Okay. I'd like to put a number on that amount of energy there. I'd like to have a number for it. What's the potential energy at the top of my desk? I can tell you the difference between the floor and the desk, but I can't tell you the number at the top of my desk. But it's got a number, clearly. It's got a number. If you have a difference in numbers, you must have numbers. And so that implies that you know that. And that implies you know that. And the problem is you don't. You don't know where the zero is. Is it the ground? Supposing I dig a hole. Is it the center of the earth? Supposing I get off the earth and fall into the sun. I can imagine there's the suns, and then there's the earths, and then there's the moons, and well, where's the bottom? The sun, well, what about the center of the galaxy? Center of the galaxy, what about the center of the local group? I mean, where's bottom? Where's the lowest gravitational point in the universe? I have no idea. The middle of the biggest galaxy? In the biggest galaxy cluster? I have no idea. And you give up. And what you say is, if I, rather than trying to find the bottom of the universe, content myself with finding the top of the universe, when I'm sufficiently far away from any mass, I'm like here. There's all stretches of space that are here and here and here and here. They're so far away from any mass, it doesn't take you anything to go another step. That's easy to find. You just got to go sufficiently far away. So what we do is we say, oh, you mean that I can ask myself, so now I'm trying to find, not from the bottom, but from the top. Now I'm trying to find that. And all I have to do to find that is I say minus G, big M, little m, 1 over my final position minus 1 over my initial, and my initial is infinitely far away. Make your initial point infinitely far away. How much energy did it take to get where you are? How much energy to get from infinity down to this table? Just put infinity in. What is 1 over infinity?
0.
Delta U, G is equal to minus G, big M, little m, over R, final, or R if you like. It's very nice. It's a negative number. How do you feel about negative energies? Isn't that horrible? How do you feel about negative temperatures? We don't get them very often here, but in Boston, minus 5 degrees, that was quite common. Nobody turned around and said, that's an impossibility. You can't have a negative average energy per particle. It's just where's the zero on your number scale? It's no big deal. So it's no big deal for this. Yes, the gravitational potential energy of this tabletop is some negative number. And the gravitational potential energy of the floor is an even bigger negative number. If you go upwards, it's positive change. If you go downwards, it's negative change. It all works. Just rather than starting your number line with 0 there, slide the whole thing so your 0 is there. And these are all negative numbers. It still works. Pardon? So your gravitational potential energy of any point in the universe should never be positive. And it is 0 when you're infinitely far away. Yeah. Which is near enough. It's actually not that far away. Yeah, exactly. And you get near enough reasonably quickly. So, okay, so now we have another thing. If I go back to my slide, I can turn around and say, oh, well, actually, there's this other thing called UG, which equals minus GMM over R. That's kind of cool. And then I say, well, I'd really like to talk about this energy stuff in terms of just, I'm sorry, so let's do these two. How am I doing for time? 15. So an 80 kilogram mass is located at the origin. Determine the potential energy of a 5 kilogram mass. So here's my 80. And here's my 5. And my 5 is at 0, 2. Here's my 5. Again, I just use my IJK to get the position. That's 2 meters. I go UG is equal to minus big G M over R. So UG is equal to minus G 85 over 2. Doesn't matter which direction it's in. There's no positive and negatives in directions for this. So this equals minus 40 times 5, 4 5s are 20, 200 G joules, which is there. Cool? Must be a negative number. Agreed? I didn't mess up, did I? Let's make it a bit more interesting. 70 kilogram mass is at 2I plus 3J plus 1K meters from the origin. What is the gravitational potential energy of a 5 kilogram mass? And this is at 3I plus 2J plus 4K. And my equation is UG is equal to minus big G, big M, little m over R. So this is a bit interesting. My UG is equal to minus G 70 times 5 over, and it's that separation. But I don't have it. So this takes us back to a little bit of our vectors. I've got to somehow figure out how I'm going to find this separation. And the trick is, let's call this R1, let's call this R2, and then let's just say this is R3. Then I look at my diagram and I say R1 is equal to R2 plus R3. Why is it that? Why is it not R1 plus R2 equals R3? What am I spotting in my diagram that says R2 plus R3 equals R1? What is it about my diagram that tells me that? Sorry? It's not a right triangle, so there's no hypotenuse, but, it's something about the way I drew my diagram and vector diagrams. The arrowheads, exactly, yes. The process of addition is putting the tail of the second vector on top of the head of the first. So these two are added together. That's the way I drew them. And this means that this R1 is the resultant. Yeah? I want to find R3, so R3 equals R1 minus R2. And that's important because when I do this, I've got to make sure I add them up or subtract them the right way. I'm going to do R1 3, 2, 4. I'm going to go minus R2. R2 is 2, 3, 1, but it's the minus of that. And I'm adding those, well, anyway. So then I go, okay, 3 minus 2 is 1. 2 minus 3 is minus 1. 4 minus 1 is 3. So then I go, oh, take this up here. So this equals 350g minus over the square root of 1 squared plus minus 1 squared plus 3 squared. So this equals minus 350g over 1 squared is 1 plus 1 is 2 plus 9 is 11. Square root of 11. So this equals, man, I hope I did this right. So this is going to be 350 divided by seconds, square root 11, enter. I'm getting 105, 105.5, 106. 106 G joules. It's going to be negative, of course, because that negative sign is in there. Oops. So let's do this next bit, which is basically gravitational potential. And what we're saying with gravitational potential is I don't want gravitational potential energy because it depends upon both masses. I'd like to get the gravitational potential of a point, and then I can put the mass I want there. So like I had electric gravitational field was like of the point, and gravitational force was of the two masses. Now gravitational potential is of the point, whereas gravitational potential energy was of the two masses. So what do? And what I do is I say, well, that is going to equal, so that is going to equal that over the little mass, which equals minus g big M little m over r over the little mass, which equals minus g big M over r. So it's kind of nice. I can do it. 3.6 kilogram block has a gravitational potential energy of that when located in space near planet Zebulon. What is the magnitude of the gravitational potential? Gravitational potential is equal to gravitational potential energy, UG over my little mass, which equals, let's have a look, that equals big G, big M, little m over R divided by little m, which equals big G, big M over R. So now let's see what I have. I'm looking for things here. So little m is equal to 3.6 kilograms, has a gravitational potential energy. UG is equal to minus 43.7 joules. What is the potential, the magnitude of the potential VG? Ah, I see. So I want to use that bit there. So I say VG is equal to minus 43.7 over 3.6, which equals 43.7 divided by 3.6 is equal to 12.1, 12.1 joules per kilogram. And as for the magnitude, so the negative sign goes to a positive, whatever. Yeah. Cool. Ooh.